Good day, grade 12 learners. Welcome to today's subject lesson. My name is Sibusiso Shongwe. This lesson is brought to you by Gauteng Department of Education in collaboration with Bono Discovery Center and is broadcast by Pagama Research and Development. Remember, we have our WhatsApp interactive number, which is 064 748 8913. 064 748 8913. Right, today's lesson is basically about interpreting sketched functions. It's a follow-up to last week's lesson where you were working with the sketching of those algebraic functions. So this week we're just going to interpret them. Right. By the end of this lesson, you should be able to determine the equation of sketched functions, identify and calculate the x and y intercept of sketched functions, calculate the average gradient between 2 points. You'd recall this one, you do it a lot in analytical or coordinate geometry. Calculate horizontal and vertical lengths or distances and extend your knowledge to maximum and minimum vertical lengths. Apply and use transformations to functions. Determine the point or points of intersection between two functions and solve inequality problems using only the graphical approach. Solve nature of the roots problems using only a graphical approach. Right, we can obviously refer to the CAPS document on page 32 and also on the exam guideline on page 6. Right, the knowledge that you should come with to this lesson: the sketching of a straight line, parabola, hyperbolic, as well as an exponential function with one or more parameters using the dual intercept method. The effect of parameters a, q, and p on functions mentioned above, as well as to determine the domain and the range of those particular functions. Right, to begin with, we are going to be looking at those 4 algebraic functions. What we want to do is to find the equation for each one of those functions. The first one, it's a quadratic function. Determine the equation of the following functions in the form of y is equals to ax squared plus bx plus c. So we want to determine that equation and then write it in the standard form that is given there. Now, with a parabola, there are 2 forms that you may be given. One form would be a form where you are given x-intercepts, and another form would be a form where you are given the turning point and an additional point. Now, if, like for an example in this one, you are given -5 and 1, those 2 values represent our x-intercepts. Because this parabola has x-intercepts that are given, in order to determine its equation, we are going to use this form. Y is equals to a into x minus x1 times x minus x2. Now, in this form, it is important to note, grade 12s, that x1 and x2 represent the given x-intercepts. So x1 and x2 represent the x cuts, or rather the x-intercepts, which means that in this case, our x1 is -5 and our x2 is +1. So what we're going to do is we first substitute the x-intercepts in the standard equation. So we will get that y would be equals to a into x minus 5 times x minus 1. If you simplify this, this would be y is equals to a into x plus 5 x minus 1. Now looking at that equation, you can see that you only need the value of a for you to be able to write down that equation. Now what we're going to do is we're going to look at that additional point which is given on the function, substitute the additional point on the equation, and calculate the value of a. So the question is now, what is the given point? The given point is this one, minus 5. And if you write this using the set of ordered pairs or the coordinate system, you would note that x is equals to 0 on the y-axis and y is equals to minus 5. So we are interested now at a point 0 and minus 5. Our x is 0, our y is minus 5. So if we substitute that on the given equation, you'll note that you'll have minus 5 is equals to a into 0 plus 5, 0 minus 1. Now if you multiply throughout, on the left you have minus 5 is equals to, on the right hand side, if you simplify the brackets, you get that a times 5 times minus 1, that should be minus 5a. Obviously, to solve for a here, we need to divide both sides by negative 5. So we'll get that a is equals to positive 1. Now that we know the value of a, we'll go back to where we see a, we substitute 1 in this equation. So where we see a, we put 1. So y would be given by 1 into x plus 5, x minus 1. When we open these brackets, we're going to get that y is equals to, using distributive law here, we get x squared minus x plus 5x and then minus 5. Simplifying that, we get y is equals to x squared plus 4x minus 5. And that represents the equation of that particular function. Y is equals to x squared plus 4x minus 5. Right, moving on. If you look at the second one, we are given a quadratic function or a parabola as well here. If you check our parabola, if we are to just look at it, you see that you are given a parabola with a maximum value of 6. The maximum value of this is 6 when x is equals to minus 1. That is what we have by just looking at that parabola. Now, because we are given that the form in which there is a turning point and an additional point, our additional point would be that point there, represented by coordinate x is 0, y is 2. So in this case, we are given a turning point and a point. If we are given a turning point and an additional point, what we need to do is we need to then write down the standard equation that would then accommodate the turning point and that particular point. So such an equation is given by y is equals to a into x minus p squared plus q. This is the turning point form of the equation of a parabola. The one that we did in example 1 was the x-intercept form. So this one is the turning point form, where now the set P is to Q represents the turning point. where the set P is to Q represents the turning point. So what we're basically going to do is, where we see P, we're going to substitute the X value of the turning point, and where we see Q, we substitute the Y value of the turning point. Now, it should be Y is equals to A into X is given by -1. So this would be X minus -1 all squared plus Q is given by 6. So this equation is Y is equals to A into X plus 1 squared plus 6. So this is the equation when we've substituted the turning point. Now we need to find the value of A. Like in the one that we worked with in example 1, what we did was we substituted the x-intercept, and then after substituting the x-intercept, then we looked for the value of A. Now here we substituted the turning point, then now we are looking for the value of A. Now how do we find the value of A? We are going to consider this at the given point. The given additional point on the graph is 0 is to 2, where x is 0 and y is equals to 2. So we're going to substitute x is 0 where we see x in the equation, and y is equals to 2 where we see y in the equation. So 2 will then be equals to A into 0 plus 1 all squared plus 6. Now if we simplify this, we get 2 is equals to A plus 6. Solving for A would be equals to, we have 2 on the left hand side, we're going to transpose the 6 to the left hand side, we're going to get 2 minus 6, which equals -4. Now that we have the value of A, we can go back and substitute it in our equation. So y would be equals to -4 into x plus 1 all squared plus 6. However, grade 12s, if you check the instruction, they said they want you to write this in the form ax squared plus bx plus c, which means that we need to simplify this equation further. Right, doing so, we're going to get that y would be equals to -4. I'm first going to open the brackets. I will have x squared plus 2x plus 1, and then I have plus 6. Now using distributive law, I'll distribute the -4. I get -4x squared minus 8x minus 4 plus 6. We now simplify this further. -4x squared minus 8x minus 4 plus 6 gives us +2. And that should represent the equation of that particular quadratic function. Now, let's summarize what we just did. We looked at 2 different hyperbolas. In the first one, we're given 2 x-intercepts and an additional point. We said if we are given 2 x-intercepts and an additional point, we use the standard form y is equals to a into x minus x1 times x minus x2, where x1 and x2 represents the x-intercepts. In the second form, we are given the turning point and a point. If we are given the turning point and a point, then we need to then look at the equation of that particular form. And such an equation is given by y is equals to a into x minus p squared plus q, where p and q represent the turning points respectively, or represent the x and the y values of the turning point respectively. Right, moving right along. Now, you see with example 3, we are now given a rectangular hyperbola. In this function, we are given the standard form as y is equals to a over x minus p plus q. Remember grade 12s. In this particular equation, p and q do not represent the turning point. P and Q represents the horizontal as well as the vertical movement of this graph. Now, first things first, if you look at this graph, you see that you are given the asymptotes. The x value of the asymptote is x is equals to 1, and the y value of the asymptote or the vertical asymptote is y is equals to 1. So the horizontal asymptote is y is equals to 1, vertical asymptote x is equals to 1. Now, if we are given the asymptotes, we know that they represent the value of p and q. So first things first, we are going to substitute our asymptotes. Y would be equals to, but first we know that x will then be equals to 1 would be the horizontal asymptote, and y is equals to 1 would be the vertical asymptote, which means that this becomes p and this value becomes q. So we'll have that this is a over x minus 1 plus 1. Now we've substituted the asymptotes. We now have to get the value of a. In order for us to get the value of a, we need a set of ordered pairs, or we need an additional point. And in this case, you can see that in the graph, we are given the additional point with x is equals to 3 and y is equals to 2. So we are interested in substituting this point. 3 is to 2, x is 3, y is 2. So where we see x, we put 3. Where we see y, we put 2. So this would be 2 is equals to a over 3 minus 1 plus 1. If you simplify this, you get 2 is equals to a over 2 plus 1. Now, simplifying this further, we can transpose the 1. We get 2 minus 1. We get 1 is equals to a over 2. If we multiply by the LCD 2, both sides, we're going to get that a is equals to 2. Now we've worked out the value of a, which means we can now go back and write down our standard equation. It will be given by y is equals to a is 2 over x minus 1 plus 1. So that would be the equation of this reciprocal function, or rather hyperbola. Moving on. In example 4, we see that now we are working with an exponential function, and they want us to find the equation of an exponential function. We are given the horizontal asymptote y is equals to 2. Remember, the horizontal asymptote represents the vertical shift. Now, or rather the value of q represents the vertical shift. Now, in this case, we are given y is equals to 2 as our asymptote. We know that this represents the value of q. So we're going to go to our standard equation. Where we see q, we're going to put 2. So this is y is equals to 2 to the exponent of x minus p plus 2. Now, the only thing that we need in order to determine this equation is the value of p, which means that we will use the set of ordered pairs, or rather we would use the coordinates that are given, the extra point that is given on the graph. So at this point, at 1 is to 6, it is true that x is 1 and y is equals to 6. So where we see x, we put 1, and where we see y, we put 6. So 6 would be equals to 2 to the exponent of x minus p. X in this case must be 1, right? So this would be 6 is equals to 2 to the exponent of 1 minus p plus 2. Now, if we want to simplify this further, we can transpose the 2. 6 minus 2, we get 4 is equals to 2 to the exponent of 1 minus p. So we can write 4 as a base of 2. If we write 4 as a base of 2, we get 2 squared, which is 2 to the exponent of 1 minus p. Using the laws of exponents, if the bases are the same, then the exponents are equal. Or if we have same bases, we can equate the exponents. So 2 is equals to 1 minus p. To solve for p, I can transpose the 2. If I transpose 1, it will be 2 minus 1 is equals to minus p. So p would be equals to negative 1. If p is minus 1, then the equation would now be given by y is equals to 2 to the exponent of x. P is minus 1, so this would be minus 1, and then plus the value of q in this case is 2. So the equation will simplify to y is equals to 2 to the x plus 1 plus 2. So that would be the equation of the exponential function. Now, let's review the last two examples that we did. It was a hyperbolic function and an exponential function, where the value of p and q in these respective curves will then represent the horizontal and vertical movement or their given asymptotes. Right, moving right along. Now that we've worked out equations of sketched functions, we now want to check the intercepts, average gradient, vertical and horizontal lengths, as well as maxima and minima. Now, I've summarized a few concepts that we're going to need for the example that we're going to do after this. X-intercepts, Y-intercepts. With x-intercepts, to find x-intercept, we just substitute 0 where we see y and we solve for x. To find the y-intercept, we substitute 0 where we see x and then we solve. Now, horizontal distance between 2 points. If you want to find any horizontal distance between 2 points, you will take the x value on the right, subtract the x value on the left. Then you'll get that horizontal distance. If you want the vertical distance, you'll take the y value at the top minus the y value at the bottom. Then you'd get that vertical distance. If you want to find the average gradient, this one is also on your formula sheet. M is y2 minus y1 over x2 minus x1. But most importantly, if we want to find the average gradient using now the functional notation, see that this is f of x2 minus f of x1. Remember, f of x2 is the same as y2 and f of x1 is the same as y1. But now we are using functional notation. Right. Moving right along. Now we are given a parabolic curve, and in this parabolic curve, the equation of the parabola, or in this particular graph, we have two functions. We have a parabolic and a linear function. The equation of the linear function is x squared plus 3x minus 4, and the equation, the equation of a quadratic function is x squared plus 3x minus 4, and the equation of a linear function is x plus 4. Right. Now, they want us to determine the length of AG. The length of AG. Now, we're going to check point A and point G on the graph and check what they represent. In doing so, we'll be able to know what to do with the length of AG. Now, if you look at point A on the graph, as well as point G on the graph, you can see that these are the points where the graph intersects the x-axis. So we call these two the x-intercepts. So A and G are x-intercepts. but they are x-intercepts of the graph of f. They are x-intercepts of the graph of f. Now, how do we find the x-intercepts? If we go back here, we said to find the x-intercepts, we substitute y with 0 and solve for x. Now, what we're going to do is, where we see y, we're going to put 0 and we solve for x, which means that we'll have 0 is equals to x squared plus 3x minus 4. So we're going to try to use inspection to find the factors here. So if we factorize this, we get that the factors of 4 are 2 and 2 as well as 1 and 4. And in this case, we are interested in 1 and 4. And in order for us to get a middle term that is positive, the bigger number should be positive. So we'd have that this is x plus 4, x minus 1. So using the zero factor law, we get that x is equals to 1 or x is equals to minus 4. Now that grade 12s, we've worked out the two values, we need to then associate them with our letters a and g. We need to trace which point is given by a 1 between a and g and which point is given by minus 4 between a and g. Now, if you check a on the graph, you can see that a is on the negative x-axis, which means that x at a is minus 4 and g is on the positive x-axis, which means x at g is equals to 1. Now, to find the horizontal distance AG, we said we're going to take x on the left minus, from here, we said we're going to take x on the right minus x on the left, which means that now we're going to take x on the right. In this case, x on the right is x at g minus x at a. So we're going to have that this is 1 minus 4, which simplifies to 5 units. So the length of AG in this case would be given by 5 units. Right, moving on. Same functions, but now we want to determine the length of ON. So we're going to check O and N on the graph. If you check O on the graph, O is the origin and N is on the graph of F, and N is where the graph of F intersects the y-axis. So we call this point X or point N the y-intercept. So O is the origin and N is the y-intercept of F. If N is the y-intercept of F, then to find that point N, we should then substitute X with 0, just like we indicated on our table here, that to find the y-intercept, we substitute X with 0 and solve for y. So if we substitute in this one, if we substitute X with 0, we're going to get that y would be equals to 0 squared plus 3 into 0 minus 4. So y simplifies to minus 4. Now that we know the value of y at n is minus 4, we can then work out the distance. Therefore, ON, the distance ON would be y top minus y bottom. Y top is at O, which is 0, minus y bottom, which is negative 4. So this would be 4 units. That would be the length of ON is 4 units. Now we also want to work out the length of CL. Let's check CL if OL is 1 unit. If you check the point C, C is on the Y, or rather C is a point on the straight line. You can see that it's on G. and it has the coordinates. If we say C has the coordinates x is to y, and it's on the straight line, our straight line equation is given by, and y is equals to x plus 4, which means that the coordinates of C are given as x is to x plus 4. That is if we substitute y for x plus 4. Those are the coordinates of C, because C lies on the straight line. Now we want to work out the length of CL, and we are given the length of OL is 1 unit. If we are given the length of OL is 1 unit, it means that x at L would be given by -1. Because if the length of OL is 1, it means x at L is given by -1, because it's on the negative x-axis. Now, if we have x at L being equals to -1, and along the line CL, x does not change. Along this line, x does not change. It means that x at L is the same as the value of x at C. Remember, I said the coordinates of C are given by C is to x plus 4. So we know the value of x at C. We want to find out the value of y. How are we going to work that out? We substitute the value of x on the equation of the function where C lies. In this case, C lies on the straight line, which means that y at C will then be given by, where I see x, I'm going to substitute it with -1. -1 plus 4. So we get that y at C is equals to +3. Now that we have y at C is +3, which means that the coordinate system for point C, it means that C will now be given by -1 is to 3. -1 is to 3, which means the length of CL in this case would be given by y top minus y bottom. In this case, y top is 3, y bottom is 0, so CL would be 3 units. Right, moving right along. Determine the length of OT if ET is 6 units. We're going to check OT. O obviously is the origin. We need to then trace T. OT. This is point T on the graph. And point T on the graph does not lie on either of the two functions. It does not lie on the parabola. It does not lie on the straight line. But we know, looking at the vertical length ET, looking at the vertical length ET, we are given that the vertical length ET is given by 6 units. And we know that y value here is given by 6 or -6. So we know that if this length ET is 6 units, it means that y here, y at E, would be given by, we know it's given by x is to y. That is the coordinate of E. E is given by x is to y. But now, because E lies on the parabola, it means that the coordinates of E are given by x is to x squared plus 3x minus 4. Because y is given by x squared plus 3x minus 4. Because this point here lies on the parabola. Now, we need to work out the length of OT. We need to work out the horizontal length OT, which means if we can find the x value at T, then we would know what the length is. But we appreciate that the x value at T is the same as the x value at E. It doesn't change. The x value at T is the same as the x value at E, which means if we find the x value at E, we would know what the x value at T is. Now, looking at this, we are given that the vertical length is 6 units. If the vertical length is 6 units, it means that y at E is given by -6, or rather it's given by +6. That length is given by +6 because point E is on the positive y-axis. So since we know that y at E is given by 6 and y at E is also given by x squared plus 3x minus 4, we're going to then say 6 would be equals to x squared plus 3x minus 4, because we know what y is along that line. Now, if we transpose the 6, we're going to get x squared plus 3x minus 10 is equals to 0. X squared plus 3x minus 10 is equals to 0. Now, if we want to factorize this using inspection, we look for the factors of 10. The appropriate ones in this case would be 5 and 2. For the bigger number to be for this value, the middle term to be positive, the bigger number should be positive. So this is x minus 2, x plus 5. Now, using the zero factor law, we get that x is equals to 2 or x is equals to minus 5. Now, we need to then trace which one would be appropriate in this case. Now, if you check t is on the negative x-axis, which means that x at t would be given by -5, because 2 is on the positive x-axis, and that's not what we are looking for, because t, the variable that we are interested in, or the letter that we are interested in, is on the negative x-axis. Now, since we know x at t, or x at E in this case, since we know x at E, we're also going to say it's the same value for x at t, because x does not change along that particular line, which means that now x at t will also be -5. So if we are looking for the distance from O to t, we're going to say now the distance OT would be given by, it would be the point on the right minus the point on the left. So it's 0 minus -5, which means OT would be 5 units. Right. Let's just recap what we did. Now, if you look at this particular problem, you are given the vertical line ET. And in that vertical line, point E is on the parabola and point T is on the x-axis. Now, we want to find the value of x along that particular line. So we just substituted 6 on the equation of the parabola, and then we solved. So we got the value of OT to be 5 units. Moving on, determine the length of KD if OR is 2 units. So we're just going to look at K and D. Try to trace K and D on the graph. Now K, you can see it's on the straight line. D, you can also see it's on the parabola. Now grade 12s, if you want to work out the distance between two graphs, because it's the linear function on top and the quadratic function on the bottom. Now what we need to do to work out the equation of that particular, or rather to work out anything about that particular length, we need to take the top graph minus the bottom graph. So generally we say the distance between two graphs is the top graph minus the bottom graph. However, we said to get the vertical distance, we said we take y top minus y bottom. Y top minus y bottom. Now if you check, y top would be the y coordinate of k, and point K in this case is a point where you are given the abscissa x and the ordinate y. Now, because point K lies on the straight line, it means that all the y values of that particular point or of that particular line would be given by x plus 4, because y is given by x plus 4. And when we look at point D, if D is given by x is to y, we know that all the points on the quadratic function are given by x is to x squared plus 3x minus 4, because the relationship between x and y is given in the equation. Y is equals to x squared plus 3x minus 4. So now, if you take y top minus y bottom, you'd be taking x plus 4 minus x squared plus 3x minus 4. Usually we would say if the distance is between two graphs, KD, we're going to take the top graph, y of the top graph, minus y of the bottom graph. Now, what is y of the top graph? Y of the top graph, given in terms of x, is y plus 4 minus y of the bottom graph is x squared plus 3x minus 4. So we take top graph minus bottom graph. That is to get the equation, or rather the vertical distance between two graphs. Now, if we simplify this, we get x plus 4 minus x squared minus 3x plus 4. Simplifying this further, we get minus x squared minus 2x plus 8. So this represents the relationship between the y values as well as the x values. Now, if you check here, in order for us to get KD, we just need the value of x. If we know what x is, then we're going to know the vertical length KD. Now, let's check what is given. We are given that OR is 2 units. Now, what we're going to do is we're going to trace where point R is so that we can associate that with the 2 units. Now, if you look at OR, R is the point on the negative x-axis. So if this is 2 units, it means that R would be given by x is minus 2 and y is 0. If OR is 2 units, it means x at R is given by minus 2. And remember, x at R is the same as x at K and is the same as x at D, because x does not change along that line. It is only y that is changing. So we know that x is minus 2. So we're going to substitute minus 2 on the given equation. Minus 2 squared minus 2 into minus 2 plus 8. Therefore, KD would be equals to, if you put this on your calculator, you'd get that this is minus 4 plus 4. KD should be 8 units. So that is how you get the value of KD. You take the top graph minus bottom graph, you get an expression, and then you look for the value of x that you can substitute in order to work out that vertical distance. Now, moving right along, we are now required to find the maximum length. You are now required to find the maximum length. Grade 12s. You are busy with calculus now, and in calculus, you are learning how to maximize and how to minimize. That would be general for all the curves. You'll know how to minimize and maximize all functions using calculus. But in grade 11, we learned that we can only maximize and minimize a quadratic equation where you have the turning point representing either the minimum or the maximum depending on the concavity of that particular curve. depending on whether it's a parabola facing down or a parabola facing up. Now, if we want the maximum length of KD, let's locate K and D. If you try and locate K and D, you see that K is on the straight line and D is on the parabola. So we've worked out in the previous slide, we've worked out the expression for KD. We said it's minus x squared minus 2x plus 8. So we would write that as minus x squared. We said it's minus x squared minus 2x plus 8. So minus x squared minus 2x plus 8. That is the expression for KD. Now, if you check this equation, you can see that this equation is the same as the equation of a parabola. This is parabolic, and they are looking for maximum length. In order for you to find the maximum length, you are going to complete a square, that is number 1, or you can use the axis of symmetry minus b over 2a, or you can use calculus if you know how to maximize and minimize. But specifically for this lesson, I'm not going to use calculus. I'm going to use the completion of the square as well as using the axis of symmetry. Now, if we use completion of the square as the first method, it means that we're now going to take KD. To complete the square, we're going to then factor out minus. So we'll get that this is x squared plus 2x minus 8. Remember, completion of the square, you take b over 2 all squared. So now this would be minus x squared plus 2x. b over 2 is 2 over 2 all squared. That is 1. So this is plus 1 minus 1 minus 8. So this will then simplify to minus x squared plus 2x plus 1 minus 9. You complete the square. For the first 3 terms, you get x plus 1 all squared minus 9. So this would be, if you distribute the negative back, minus x plus 1 all squared plus 9. So you've worked out now, or you've completed the square to change this equation and write it in terms of the turning point. So now we can conclude that therefore maximum value of this, max KD, would be equals to 9 units when x is equals to minus 1. So that is the maximum, because what we've now worked out is that this parabola would turn at minus 1 and 9. So this parabola turns at minus 1 and 9. X is minus 1 and y is equals to positive 9. Positive 9. So this now represents the maximum value of this. It occurs when x is equals to minus 1. Now that is the first method. The second method that you can use, I'll just squeeze this in, method B. You can find the x value to which the maximum occurs. The maximum occurs, max occurs at x is equals to minus b over 2a. So we're going to substitute negative b is given by negative 2 over 2, a is minus 1. So x would be equals to negative 1. So now we've determined the value of x to which the maximum occurs. So in order to get, I'll just try to squeeze it here. In order to get the max KD, what we're going to do is we substitute on the original equation, we substitute minus 1. So this would be minus into minus 1 squared minus 2 into minus 1 plus 8. Now, in doing so, we're going to find that this is equals to 9 units. So max KD is equals to 9 units. Remember, for those who have done optimization in calculus, you can use the calculus concepts here by just differentiating dkd dx and equating that derivative to 0. Find the value of x to which this maximum occurs, substitute it back, and find the corresponding value of y. Right, moving on. Calculate the average gradient of line AB if the coordinates of B are 2:6. This is just basic gradient calculation. So what we're going to do here, we're going to check, we want the average gradient of AB. So we need the coordinates of A as well as the coordinates of B. The coordinates of A, in this case, we've worked them out. We got that A is minus 4:0. We've worked them out. And then B is given by 2:6. So we're going to be using gradient is equals to y2 minus y1 over x2 minus x1. So our y2 minus y1, in this case, it should be 6 minus 0. If we say this is xy, 2, 2, 1, 1, it will be 6 minus 0, 2 minus 4. So the average gradient would be equals to 1. Either way, from this equation here, you see that the gradient of that line is equals to 1. So we've worked that out as well. Right. Now, grade 12s, we move away from lengths. We look at now transformations. With transformations, we're going to focus on 3 things: translation, reflection, as well as stretching or squashing the function or multiplying a function by a constant factor of a. Now, with translation, what happens is that you are going to move a graph or a point upwards or downwards. So upward and downward movement is governed by the value of Q. Or you'd be moving the point to the left or to the right, and that would be governed by the value of P. Now, looking at this table, you see that if you want to translate any point given by axis to y vertically, what you're going to do is you leave x as it is, but on the value of y, you're going to add q because the graph moves upwards. Now, the effect of the equation, in the equation, a constant q would be added. If you check, our old equation was y is equals to f of x. Now, this is given by y is equals to f of x plus q because every point on the graph moves upwards. So there is the effect there. The implication is that the graph shifts up when q is positive and shifts down when q is negative. And the graph is in accordance with the sign of q, which means if q is positive, the graph would also move up to the positive y-axis or move up. If q is negative, it moves down. Right, looking at the horizontal movement now only affects the value of x because you are moving with respect to the x-axis. Now, in order to get that shift, what we do is we leave y as it is, and we're going to add a parameter p to the value of x, which means that all the points, all the x values are going to shift by 2 units, either to the left or to the right. Now, if you check here, the point will then be, the point x is to y changes to a point x plus p is to y. And in the equation, where you see x, you're going to put x plus p. X is replaced by x plus p. That's very, very important. Now, in the equation, obviously, you substitute x plus p where you see x. Now, with respect to the shift, if p is positive, the graph moves to the left. If P is negative, the graph moves to the right, which means that the movement or the shift is opposite to the sign of P. If P is positive, the graph moves to the left. If P is negative, the graph moves to the right. Now, let's move on to reflection. You reflect about the x-axis or about the y-axis. If you reflect with respect to the x-axis, y becomes negative. If you reflect with respect to the y-axis, x becomes negative. So you can see on the set of ordered pairs, if a original point was given as x is to y, and you are reflecting with respect to the x-axis, then x remained the same, but y became negative. With respect to the functional notation, you would have that now the new function would be given by minus the original function because y becomes negative. Now, what happens on the graph is that the graph flips about the x-axis. With respect to the y-axis, if you reflect with respect to the y-axis, what you do is x remains the same, y remains the same, and x changes sign because you are reflecting with respect to the y-axis, which means that all the x values are going to be negative. So you can see here that a point x is to y became a point minus x is to y. And now what you do is you replace x with minus x. And the graph flips with respect to the y-axis. Now to stretch or to squash, what we basically do is we multiply all the terms in that equation by a constant factor of a. And we can see the effect here that if a is positive, the graph is stretched away from the x-axis. And if a is also negative, it stretches away from the x-axis. But if a is between -1 and 1, you find that the graph is squashed. Now, it's important to note here that also the negative will reflect the graph with respect to the x-axis. Right, now that we've looked at the table that summarizes transformations, let us look at some questions. Example 1. You are given f of x, it's an exponential graph. F of x is equals to 2x minus 1. In each of the following cases, determine the equation of g and describe the transformation from f to g in weights. Now, what we want to do here is find the equation of the new function after the transformation has taken place, and then we describe that transformation in weights. Now, if you look at this g of x, it says g of x is equals to f of x minus 3. So where we see f of x, we're going to put the original equation that is given. So this would be 2 to the x minus 1 minus 3. So we find that the new equation would be 2 to the x minus 4. Now, we want to describe the transformation. What happened here is that you moved this graph. 2 to the x is the same for both f of x and g of x. But now minus 1 changed and became minus 4. Minus 1 changed and became minus 4. Why would what happened for minus 1 to change and become minus 4? It means that it was moved downwards by 3 units. So we're going to say that describe the transformation from f to g. We're going to say f is shifted 3 units down to obtain g. That would be the transformation. We shifted the graph of f by 3 units down. Now, second one, we are given g of x is f of x plus 2. You can see that now this transformation is on x, or on the x-axis, or on the values of x. Now, what are we going to do here? To get g, instead of having f of x, x changes and becomes now x plus 2. So where we see x, we're going to put x plus 2. So our g of x will then be equals to, in the original equation, where we see x, we put x plus 2 minus 1. Now, from this equation, you can see that the graph, what happened is that we moved all the points on the graph by 2 units to the left. Remember, on the table, we said if p is positive, we're going to the left. If p is negative, we're going to the right. So we say that f is shifted 2 units to the left to obtain g. That's what we have. Now, last one, we are given minus f of x minus 3 plus 3. If you check here, we have 3 transformations. We have a transformation here because of the negative. We have a transformation here because of x minus 1. We have a transformation here that represents the vertical movement. So we're going to write the equation first. Our equation in this case would be given by g of x is equals to, where we see f of x, we should have a negative first. So this is minus, obviously our f of x is 2x minus 1. But where we see x, we should put x minus 1. So this is 2 to the x minus 1, minus 1, and then plus 3. So what I basically did was, where I see x, I put x minus 1, and I reflected this with respect to the x-axis. Now, I'll simplify this by opening the brackets. G of x would be minus 2 to the x minus 1 plus 1 plus 3. Now, if you look at this, you get this as negative 2 to the x minus 1 plus 4. Now, if you check from the original, if you compare g with f, you can see that instead of 2 to the x, you have minus 2 to the x minus 1. So there is a translation of 1 unit. There is also a reflection about the axis, but there's also a vertical movement. So what we can say here is that f, we can say f is reflected about the x-axis, then moved 1 unit to the right, and we want to check the vertical movement. The vertical movement is from minus 1 to 4. So to move from minus 1 to 4, you have to move 5 units, and 5 units upwards to get g. So that is what we basically did with the last function. But first, you find the equation and then you describe the transformation. Right, moving on. Still on transformations. We are now given a hyperbola and we want to know what happens to this hyperbola. Now, what we're going to do is we're going to check the first question. It says, write down the equation of the asymptote. They want you to write down the equation of the asymptote. You are not describing the transformation. They are giving you a new graph which is related to the one that is sketched, but it was transformed. And then they want you to describe the parameters of the new transformed function. Now, there are 2 methods of doing that. What you can do is you can find the original parameters and then you will transform them based on the given transformation. Or you derive a new equation after getting a new equation, then you're going to get the value of the parameters. Now, with method A, I'll just quickly write down the two methods. With method A, what I'm going to do is I am going to write down the asymptotes of f, the original function. So asymptotes of f, the asymptote of f will be x is equals to 1 and y is equals to minus 2. Those are the asymptotes of the original function. Now, after transformation, I can now work out the asymptotes of g. Remember, g is related to f by that equation. G of x is f of x plus 2, which means that now we are moving all the points 2 units to the left, which means the asymptotes are going to shift 2 units to the left. So the x asymptote will then be x equals 1, and you shift that 2 units to the left, you get minus 1. And that of y stays the same because you were moving this you were only transforming this on the x-axis. It was horizontal movement. The graph was moved only horizontally, so the vertical asymptote remains the same. Now that is method A. With method B, what you can do is you can do what we did on the previous slide. We find the equation first. So we know that g of x is related to f of x in this form. So what you do here, you see that instead of substituting x, to get g, where we see x, we're going to put x plus 2. So this would be equals to 2 over x plus 2 minus 1 minus 2. So the new equation g of x would be given by 2 over x plus 1 minus 2. So what would be the asymptote of g now? The asymptote of g would be given by the x asymptote is x plus 1 equals to 0, x is equals to minus 1, and the vertical asymptote is given by y is equals to minus 2. Now, if you check the answer and compare it with the one that I got here, you see that the answer is the same. Now, with method A, what I did was I found the asymptotes for the original function, and then I transformed those asymptotes using the given transformation. Now, with method B, I wrote down the new equation of g now, which was transformed, which was f transformed. After transforming f, I get g. After getting the equation of g, I get the asymptotes from that particular equation. Now, moving on, write down the domain and range of h. Write down the domain and range of h if h of x is f of x minus 1 plus 3. Similarly here, what I'm going to do is I'm going to use two methods. The first method, what we do is we're going to find the domain and range of the original function f, and then we check the movement, and then we're going to move the domain and range with respect to the given transformation to get the domain and range of h. Now, method A, what I do is here, we're going to look at the domain and range of f. So domain and range of f. Since this is hyperbolic, we know that the domain would be x an element of all real numbers, but x cannot be equals to 1. It should take all real numbers except that asymptote, because the graph is not defined there. And the range, in this case, range, you take all real numbers from minus infinity to infinity, but y should not be equals to minus 2. That is the domain and range of f. Now, to find the domain and range of g, for g, what are we going to do? We're going to transform the domain and range of f using the given transformation. If you check the transformation, all the points are moved 1 unit to the right and 3 units upwards. So for x, I'm going to add 1, and for y, I'm going to add 3. So the domain and range for g would be x, an element of all real numbers, but x cannot be equals to 1 plus 1, which implies that x cannot be equals to 2. And then the range, y, an element of all real numbers, but y cannot be equals to, now, minus 2 plus 3, because all these points are moved 3 units upwards, which means that this would be 1. It's not equals to 1. So we found the domain and the range using method A. Now for method B, what we're basically going to do is we transform the function, and then from there we get the domain and range of the new function. So h of x is equals to, on f of x, where you see x, you put x minus 1. So this is 2, x minus 1 minus 1. And then minus 2, and then plus 3. So h of x would be 2 over x minus 2 plus minus 2 plus 3 is plus 1. So from this new function, g, or rather h in this case, it's not g, it's h, sorry. For this new function h, the domain would be x, an element of all real numbers, but you should exclude the asymptote. The asymptote in this case is x minus 2, which means x is equals to 2. So you should not have 2 in this case. So x cannot be equals to positive 2. And then the range should be y, an element of all real numbers, but now y should not be equals to the vertical asymptote in this case, which is 1. Now, if you look at both the solutions, they are exactly the same, using method A as well as method B. I repeat for the last time, with method A, you're going to find the original domain and range, or the domain and range of the given function f, and then from there you look at the transformation, you transform the domain and range to get the domain and range of g, or h in this case. With the second method, what we do is we write down the equation of h using the transformation. After writing the equation of h, we find the domain and the range from the equation. Right, moving on. If another function r is defined by r of x is f of x minus 3 plus 7, determine the coordinates of the point of intersection of the asymptotes of r. If you check from the original f, the point of intersection of the asymptotes should be 1 and 2. Because you can see that it's also given in the graph. The point of intersection should be 1 and minus 2, because x is 1 and y is minus 2. The horizontal asymptote and the vertical asymptote in this case. Now, if we want to get the point of intersection for g, if we want to get, this is for f, if we want to get it for g, in this case is r, not g. If we want to get it for r, what should we do? We should move these points according to the transformation that is given. That is method A. So what is the transformation? All the values of x should move to the right. So I'm going to add 3 to the value of x, and I'm going to add 7 to the value of y. So the point of intersections for r of that asymptotes would be 4 is to 5. What I did is I wrote down the coordinates of the point of intersection, and then I transformed it using the given transformation. Alternatively, we said we can write down the equation of r. R of x should be given by, that's the second method, method B. R of x should be given by, what we do is where we see x, we put x minus 3, and where we see y there, we're going to put that plus 7. So R of x, we're going to have that this is 2 over, where we see x, we put x minus 3. So this is x minus 3 minus 1. And then we had minus 2. We're going to move that vertically with 7. So this would be 2 over x minus 4 plus 5. So now from here you can see that the point of intersection would be 4 as well as 5. So it's the same as that. It's exactly the same. Right, moving right along, I think we are done with transformations. Now we move to interpretations and inequalities. We're going to look at now our table for inequalities. Now here what we're going to do is, you are used to solving inequality problems algebraically when you work with your algebra. But now we should also know how to do that when we work with graphs, to do it graphically. So in order for us to do it graphically, we can use this table as a guideline. If you check, the first part is just single bounded functions, the functions that go on their own. F of x is greater than 0. This is just trying to tell you, remember, if they say greater than 0 means positive. Greater than 0 means the number is positive. But if they now say y greater than 0, with respect to the Cartesian plane, y is greater than 0 is here. It occurs above the x-axis. And y is less than 0 occurs below the x-axis. That is what we need to note. And then we are given the second part, which is the comparisons. Comparisons, we're going to look at, these are our comparisons. We're going to look at two functions. We compare them. Now, in order for us to compare them, we need to know the starting point. The starting point would always be where they are equal. So we use points of intersection as reference. We always use the points of intersection as reference. We start with the functions where they are equal, and then from there, we're going to check what happens to them. So how do we compare them? We start with where they are equal, and then we say f of x greater than g of x. That is where f is above g. F of x less than g of x. F is below g. F of x minus g of x. F is above g, but the distance between them is 1 unit. Now the last part, which is a bit more challenging, speaks to combination. Now, how do you pick up that it's a combination? A combination would give you, or you'd be given two functions, and you are going to either multiply or divide those functions. Then you know you are combining them. And the combined effect should be given by something that they are going to give you. Like for an example, if they say f of x times g of x is positive, they are trying to tell you that the combined effect of these graphs should be positive. Even if they divide it, they are trying to tell you the combined effect, because if you divide and multiply, you get the combined effect of the functions. It should be positive or negative. Now, what is key here? We said with the points of comparisons, we're going to check the points of intersections. The point of intersections are going to be used as reference because they are going to tell us where the graphs are equal. So we will know what happens, or we will know whether one graph is greater or one graph is less than the other when we start at where they are equal. Now, With combinations, what is the starting point? The starting point is we start where both graphs are equals to 0. We start where both graphs are equals to 0. We start where f of x times g of x is equals to 0. So we start on the x-intercept. So here we're going to use x-intercepts as reference. I repeat, you are going to check where the graphs intersect the x-axis because that is where we start. Or rather, that is where the combined effect is equals to 0. So we start with where the combined effect is equals to 0, and then from there, we can know whether the combined effect would be positive or the combined effect would be negative. Right, moving right along, we are given this quadratic function as well as a linear function. We want to find the point of intersection. In order for us to find the point of intersection or the coordinates of point C, the coordinates of C, in order for us to find the coordinates of C, we need to work out the point of intersection because C is where the two graphs intersect. So we're going to find the point of intersection by equating f of x to g of x. If we do that, we're going to have minus x squared minus 2x plus 3 is equals to 2x plus 6. Transposing, we get minus 2x minus 4x minus 3 is equals to 0. So this would be, if you divide by negative, x squared plus 4x plus 3. Working that out, we get x, and then we find that the factors of 3 are 3 and 1. Both of them should be positive. So x would be minus 1 or x would be equals to minus 3. Now we're going to try and trace the one for C because the points of intersection there are two of them. There's A and C. So the one for C should be negative 1 and the one for A would be minus 3. But we are interested in the one for C. So what we're going to do is we substitute this in any of the two equations that we were solving. So we now want to find y. Y would be equals to 2 into, if we use a straight line, minus 1 plus 6. So this would be equals to 4. So the coordinates of the point of intersection C would be given by minus 1 is to 4. That is how we find the point of intersection. It's like you are solving the two equations simultaneously. This is the application of simultaneous equation that you learned when you were doing algebra. Right, moving right along. Right now, we want to determine the values of x for which f is greater than 0, g is less than 0. So we said if they say this is a single bounded function, if they say f is greater than 0, we want a region where the graph is above the x-axis. The graph of f is above the x-axis. Now, if you look at the graph of f here, you can see that these are the x-axis. And the graph of f is above the x-axis on that particular point. We've drawn the graph being above the x-axis. Now we need to state the values of x for which that occurs. Now, in order for us to find the values of x to which that occurs, what we're going to do is we're going to check now from left to right. You can see that it occurs when x is in between minus 3 and 1. That is where we get f of x being positive. Now the last one, we want to find where g of x is less than or equals to 0. So it says here you want the graph of g, the straight line, when it's on the x-axis or below. Now if you check here this portion of the graph, you can see that that portion of the graph is below the x-axis. So because that portion of the graph is below the x-axis, that is where our solution would lie. So we want to find the values of x to which the graph is below or on the x-axis. So it happens when x is less than or equals to -3. So those are the two solutions for the single bounded functions. Now, moving right along. Now, if you check this one is now comparisons. We are now comparing two functions. The first one, there's an error here. This part should not be there. The part greater than 0 should not be there. We should have f of x. This problem is f of x greater or equals to g of x. It's a typing error there. So we want to solve where f of x is greater or equals to g of x. We are comparing the two. Remember, I said if you want to compare, the reference point would be the point of intersection. Now, what I'm going to do here, I'm going to go straight to our reference and draw vertical lines, just so that we see the point of reference. The reference is this one, and the reference is that. So we have -3 and we have -1. Those are our points of reference. So what we're going to do is we're going to check how the two functions behave on the left-hand side of the points of intersection, in between the point of intersection, and on the right-hand side. So we're going to check what happens here on the left. We're going to check what happens in between, and we're going to check what happens on the right. Starting from left to right, if you check now, the graph of, this is the graph of G, this is the graph of F. This is the graph of F, and this is the graph of G. This is the graph of F, and that's the graph of G. Now, on the left-hand side, we want here where F is above or on G. That is what we are looking for. So, when we look at the left-hand side, we can see that G is above here. This is G above, G is above, and F is below. If we look at in between the 2 points of intersections, between -3 and -1, you can now see that F is now above and G is below. That is where we want the solution. So the solution lies between -3 and -1. That is where our solution set would lie in this case. Now, if you look at the next one is a bit tricky. They said f of x minus g of x is less than 0. This is also a comparison question. What we do is we transpose g of x to the right-hand side. We get that this is f of x less than g of x. So we want the region where the graph of f is below. Now, if you check here, f is below g. We're going to look at the left-hand side of the point of intersection. You see that g or f is below g, or g is above f in this case. So this occurs when x is less than -3. Also, when you continue, you see in between the point of intersection, f is above. And on the right-hand side of the point of intersection, g is here and f is there. So you see that now g is above. G is above when x is greater than -1. So that is what we were basically looking at. Now, I repeat again the problem-solving strategy. We are looking at comparisons. We are comparing two functions. So we're going to now draw vertical lines on the point of intersection. And then you're going to read from the left-hand side to the right-hand side. You read from the left to the first point of intersection. You read in between the 2 points of intersection, and then you read from the last point of intersection to the right-hand side. Right, moving on. Now, these ones are combinations. Now, remember with combinations, you want the combined effect of the graph. You want to know when you have positive or when you have negative. Now, looking back at the rules of signs, we know that if you have positive multiplied by positive or positive divide by positive, you're going to have that the combined effect here would always be positive. If you divide a positive number by a positive number, you get a positive. Or multiply a positive number by a positive number, you get a positive. Similarly, if it's if it's negative signs, you're still going to get a positive, as long as the signs are the same. But to get a negative, you need to then focus on different signs. Positive times negative would always give you a negative. And positive divided by negative would always give you a negative. So that is what we will focus on. That is the combined effect. We're going to check whether the graph is positive or the graph is negative. But it's not on its own. You're going to be comparing, or rather combining, two functions. Where the combined effect, like for an example, if you check the first one, f of x times g of x is greater than 0. The combined effect of these two functions, f and g, should be positive. In the second one, the combined effect of these two functions, f and g, should be negative or 0. So I said the reference point in this case would be where the graphs are equals to 0. Now, if you check here, both the graphs are equals to 0. If you check here, one graph is equals to 0. So you're going to use the x-intercepts of the graphs as reference. So I'm going to draw vertical lines on the x-intercept so that I can find the points of reference. Now, with the first one, what I'm going to do is I'll draw a number line. The first point of reference is -3. The other point of reference is 1. And then here, I have the product or the combined effect. The combined effect here is 0. The combined effect here is 0. Now, I'm going to go back to the functions and check where one graph is above and the other is below. Now, the first one, you can see that f, you check where f is positive. F is positive here. The graph of f is above the x-axis here and below the x-axis there. Below the x-axis there. And when you look at the graph of g, it's below the x-axis here and above the x-axis there. So what you want to get now is the combined effect. When you combine both the graphs, reading from left to right. When I read from my left-hand side here, you can see that both the signs are negative, which means the combined effect would be positive. When I look at them in between, I can see it's positives all over, so both would be positive. And when I look at the last part, I can see that this one is negative and that one is positive, which means the combined effect would be negative. Now, to get the solution, the first solution they wanted where the combined effect is positive. So for the combined effect to be positive, we are looking at this side and we are also looking at in between the 2 points. So x would be less than -3, or x would be in between -3 and 1. Alternatively, someone can just say x is less than 1 that way, but x excludes -3. So all the values that are less than 1 excluding -3. Right, because of time, grade 12s, we won't be able to do the rest of the problems. Thank you very much for watching this lesson. Please remember to wear your masks, to sanitize, and also to practice mathematics. Till next time, bye-bye.